I'll just jump into it. My name's Ethan. I'm a third year university student. I'm studying electrical engineering. I'm in charge of the Getaway Special Student Satellite Team at Utah State University. So I'm just going to talk a little bit about who we are, what we're doing. I'll talk a lot about the last satellite that we worked on, kind of the some of the software behind it and some of the hardware behind it. I'll touch briefly on the current satellite project that we're working on, and yeah, I'm happy to answer any questions there. So yeah, I'll just jump into it. The GAS team is a group of fully undergraduate students. We design and test and build and operate these CubeSats all by ourselves. And a CubeSat is actually, I have a model here. Um, they're pretty tiny satellites. This is a 2-scale model of the last satellite that we made. You can pack a lot of punch into a tiny form factor like this. Yeah, this is the last one that we made. I want to talk about this one a little bit. It was called GASPACS. And so this was the Getaway Special Passive Attitude Control Satellite. Now, back in the day, when we first wanted to get into making satellites, we were really excited and we just kind of wanted to make a simple one to take pictures of the Earth, right? But the problem with that is when your satellite is going through orbit, it's only pointing up it's only pointing down at the Earth half the time, and the other half the time it's pointing up towards the air, right? And so it's hard to know exactly when to snap a picture. And so then we started looking into methods of stabilizing the rotation of the satellite, kind of slowing down the rotation of the satellite. And then eventually we kind of pivoted, and that stabilization method became the primary focus of the satellite. And so I'll talk a bit about why it's called passive attitude control satellite here in a second, but we were a part of a NASA program called the CubeSat Launch Initiative. And I'll talk about that too here in a minute. But we proposed it to NASA in 2013. We got approved for the grant. We were in development hell for a little bit. And then you can see it wasn't until 2021 we actually got the satellite completed. We sent it off to NASA. The way they got our satellite into orbit is they launched it on an International Space Station resupply mission. And then once it's on the ISS, they just kind of eject it out into space. And then that's how the satellite gets into orbit. So it was launched at the end of 2021. It was deployed a couple weeks after that, and then eventually it was in orbit for 4 months, and then it deorbited in May of that year. So um, I'll just touch briefly on that NASA grant program because we like to shout them out because they're very nice to us. It's a a grant that any university or nonprofit can apply to in the US. You basically apply with a CubeSat idea, and if NASA likes your idea, they think it has educational merit, then they'll approve you for the grant and they'll pay for the cost of your launch, which is really cool. They don't pay for any of the cost of the components. Still building this cost us like $50,000, but actually launching something of this size costs closer to $200,000 to $300,000, and we definitely don't have that kind of money. So that's a pretty cool opportunity that we have to participate in this program and have NASA pay for the launch there, which is pretty cool. All right, so more about gas packs specifically. So the way that we wanted to stabilize the satellite is we basically had this inflatable arm, kind of like a balloon, that popped out of the satellite, and then that would cause some drag that would help stabilize it. So I've actually got one of the balloons here. You can tell it's pretty long. It's actually a meter long. It's You can tell it's kind of that balloon consistency. The idea is you put 2.5 psi inside of the balloon here. We call this the aero boom. And then relative to Earth's atmospheric pressure, which is like 13 psi, 2.2 really isn't anything, right? So you're able to like fold it up and like compress it and shove it inside of the satellite, right? But then once it's up in orbit in the vacuum of low Earth orbit, right? 2.2 psi is a lot of air pressure relatively. And so it's going to want to expand like as a balloon, basically. Once it's up in orbit, we're able to allow it to pop out of the satellite. And then that arm is able to catch a lot more extra drag in the direction that the satellite's going. And then that's able to slowly slow down the rotation of the satellite. So that's the idea behind gas packs. Here's a cool video. I don't know if you guys can see this, but this is what it kind of looks like to have the arm pop out of one of the satellites here. This is in our vacuum chamber. This is one of our test runs that we ran. All right, I'll run that again. Yeah, so that's what the arrow boom was. That's what it did. You can tell there's a picture right there of us kind of folding it into. There was the whole top third of the satellite here was just a little container that we packed the arrow boom inside of and just kind of folded it up and stuck it in there. So yeah, that's GasPacks. I want to talk a little bit more specifically about the software that we used and the kind of custom electronics that we made to get GasPacks working. And full disclosure, if you were looking at the timeline, you saw it went up and it was in orbit in 2022. I actually wasn't in university in 2022. I wasn't on the gas team. So I am in charge right now, and I do know a lot about GasPacks, but just take everything I say with a grain of salt. And if you have any super specific questions, I might have to get back to you on that. But anyway, just wanted to put that out there. Now, as far as when you're building a CubeSat, I mentioned this cost us around $50,000 total to build. Um, Normally, when you're building a CubeSat, you'd probably buy your flight computer from a company that makes them specifically for CubeSats. There's one that EnduroSat makes. They're a company. We used their solar panels and their batteries on GasPacks. They're probably the cheapest in the market. Pumpkin Space makes a computer that can run you up to $10,000. Not ideal, right? And these are just a couple companies that have their prices publicly listed. Most others you have to ask for a quote, and it's going to be around that range, right? 7, 8, 9, upwards of $10,000 just for the computer, which isn't ideal, right? If we're a university team, we don't have that much money. So the idea is instead of using one of these really expensive computers, what if we switch it out and we use a Raspberry Pi instead, right? Depending on like the RAM that you want to get on the Pi, it'll run you anywhere between 10 and like $80, depending on the time of year you buy it, right? It's a lot cheaper. It's a lot more user friendly. Anyone who's like a first year student can just jump in to the project and start coding in Python immediately if they want to get involved. And we ended up flying a Pi Zero on the satellite. And that's actually a lot smaller than some of the other computers. So there's some bonuses to using a Raspberry Pi. Now, as nice as it sounds, there's also some disadvantages to using a Pi. So just some common disadvantages of a Pi here. A lot of times when you're up in space, you're going to get some bit flips from alpha radiation from being out in space. If you haven't seen, there's a really cool Veritasium video where he talks about bit flips. Go watch it if that sounds interesting. Basically, there's some erroneous behavior that can happen when you've got random access memory up in space. It can kind of have problems every now and then. Also, Pis are very power hungry. A lot of the more expensive CubeSat computers that you can buy off the shelf are going to try to optimize out those things that you don't need, and it's going to be able to be a lot more efficient with its power usage, right? A Pi isn't really designed to do this, and so it's just going to be taking a lot of power. And when you only have 5 solar panels on something like this, that's your only power generation. It's kind of tough to power a Pi like that. Another reason you'd probably want to buy your computer is they've got a lot of safeguards built in, they've got a lot of redundancy built in, and you really have to try hard to write code that's going to break your satellite. But if we write it on a Pi, bad code is bad code could easily mess up the mission. It could easily screw stuff up. It could easily break stuff. So that's another thing to consider. Also, when you're in low Earth orbit, you are alternating back and forth from negative 65 degrees Celsius to 125 degrees every 45 minutes, right? It'll spend 45 minutes on the day side of Earth and then 45 on the night side of Earth. And it'll be jumping back and forth and oscillating between those extreme temperatures very rapidly, which can be bad for your computer depending on how it's set up. So that's another thing you want to consider if you're going to try to use a Pi for your flight computer. As far as how we went around some of these risks, for our SD card, we actually you can buy a pretty expensive like alpha radiation resistant SD card that's resistant to those bit flips. You can also get really fancy and use some radiation resistant coating to like go around the entire Pi if you're really worried about it. As far as power consumption, there's not much you can do about that. That's just kind of the trade-off for using a Raspberry Pi as your flight computer. So you can maybe try to optimize out some of that, some of those inefficiencies But at the end of the day, that's just kind of the trade-off there. As far as redundancy goes, write really, really good code is the idea, and have a lot of eyeballs on it to make sure that it's going to be good and to make sure that it's not going to ever enter a state where you're in like an infinite loop or you're stuck or something like that, or something's not responding and then your satellite dies. So also, I'll talk about the watchdog. That's an auxiliary microcontroller that helps with some redundancy. I'll talk about that in a little bit. As far as the operating temperature, as much as this is kind of a problem, we didn't worry about it too much on gas packs. Reason being, if you've ever run a Pi for like a couple hours and then try to touch the CPU and it doesn't have a heatsink on it, you're gonna burn yourself, right? They run pretty hot. But so that kind of deals with the cold of being on the night side of Earth. When you're on the day side, we're more worried about it overheating, but the Pi's not uh, outside. It's going to be inside the satellite, right? So it's not going to be in direct sunlight. So it's not going to be getting a whole lot of heat from there. It's also not in direct contact with any external parts of the satellite. So it's just kind of insulated from that. We might do some extra measures to make sure that it's not going to be overheating on our next satellites, like some actual insulation in there. But we'll see. That's something we're still looking at. So. All right, I want to touch real quick on the flight software that we use for GasPacks. This isn't exactly my area of expertise, but if you are curious and you want to go take a look, all of the flight software that flew on GasPacks is still on our GitHub publicly, so you can go take a look at it if you want. It was mostly written in Python for the same reason I mentioned earlier. If anyone new to the team can just hop in and even if they don't know Python, Python's pretty easy to pick up, right? And you can just jump into helping writing the code and helping making progress on the satellite just like that. We did write a couple of I think our radio transmission drivers were written in C, just because they needed to be a little bit more robust, I guess, was the reasoning behind that. But yeah, most everything else was written in Python. So real quick, I'll run us through kind of the state of the satellite as the flight software is running. So first thing is it's going to be on the rocket, right? And it's actually not going to be the computer is not going to be turned on while it's in the rocket. It'll have a physical switch when it's like in the little compartment that'll be pressed down, and then that switch will physically disconnect the batteries from like the 5-volt bus and stuff like that. And so the Pi won't be able to be powered on at that point. Once it's ejected out into space, though, that lever is going to be disengaged and it is going to reconnect the power to the Pi. And then once it's ejected out into space, that's when it enters boot mode. And so in boot mode, actually the rules are when you're ejected from the International Space Station is you have to wait 30 minutes before you actually turn on your satellite. And so basically once the Pi power is on, it's just going to wait, do nothing for 30 minutes. It'll start a timer. And then once that 30 minutes is up, it's sufficiently far away from the space station. Then it enters antenna deployment mode. And so we had a little wire antenna that popped out of the satellite here that we were able to use to talk to the satellite. So that is just activated, and that pops out of the satellite first. And then after that, we've got a couple different modes to handle the aero boom deployment itself. So first, it'll run some checks. It'll in pre-aero boom deployment mode, it'll check, okay, did the antenna deploy okay? Is that working? Is everything turned on? Is anything obstructed? Just kind of quadruple check that that we are like in fact outside of the rocket, because if that were to deploy inside of the rocket, that'd be pretty bad, right? So it does all those checks, and then it'll actually deploy the aero boom. The way that works, I should have put a picture in here actually, because I don't know if I can explain this with words very well. But basically, this compartment will be tied down, and with these holes right here, you'll have we basically use some high quality fishing line actually to tie everything down, and then at somewhere inside of the satellite here, you tension that fishing line, you run it over just a little piece of wire. And then when you want to deploy the aero boom, you run a current through that wire. That'll heat up the wire, right? And then the wire will be in contact with the fishing line. It'll heat up, fishing line will burn, it'll break, the knot will break, and then it's no longer holding the compartment down. So then it's able to pop out after that. So anyway, that's how it deploys the aero boom. And then once it's done with that, it just does some final checks to verify, did the aero boom deploy okay? Make sure everything's good, make sure everything looks fine with that. And then after that, it's just going to continuously enter transmission mode. And so it'll be sending out some telemetry as it goes, right? GPS data and stuff like that. And then also when it's in that mode, it can, I don't remember if we had to manually command it to take pictures or if it was automatically doing those on its own. I don't recall off the top of my head, but in that mode, that's where it would be taking pictures there. Now, I mentioned I would come back to the watchdog. Like I said, this is an auxiliary microcontroller on the electrical board that we have the Pi hooked up to. It's a very simple code that it's running. All it's doing is it's looking for a half hertz signal coming from one of the GPIO pins on the Pi. So that GPIO pin will just be driven high for a second and then low for a second and then high for a second and low for a second. And then as it'll the Pi will always be running that signal there. And then the reason it's doing that is if at any point it takes too long to respond to something or something gets stuck, it gets stuck in a loop, and it's not able to transmit that half hertz signal, the watchdog is going to catch that the signal isn't coming from the Pi. If it ever goes 4 seconds without seeing that signal from the Pi, it'll shut it off. And so the Pi isn't actually directly connected to the 5 volts power coming from the battery. It's ran through a transistor that the watchdog controls. And so if anything goes wrong with the Pi, the watchdog is just there to add another level of redundancy. So if something goes wrong, it can switch that transistor, turn the Pi off basically for like 5 seconds, turn it back on. That reboots it. Hopefully it's able to enter normal operation after that. And then worst case scenario, if something goes wrong with the watchdog too, in case you're curious, the way that transistor is set up, the watchdog can only turn the Pi off if the watchdog drives that signal high. And so if the watchdog dies, the Pi is just going to be continuously plugged into the 5 volt supply. So it'll all work out there. Now, I do want to talk a little bit about the electrical board too, because I think this is pretty cool. And this is more my area of expertise. Now, this is the electrical board. I actually have it right here. This is our engineering model that we used when we were testing gas packs here on the ground before we actually assembled the final version and put it up in space. So this is what it looks like. It was mostly just a bunch of peripherals that allow the Raspberry Pi to control everything. And I'll kind of run through what each of the individual bits are here. So at the bottom, this part right here, there's all these pins on the back. That's called the PC104 stack. That's basically just CubeSat jargon for, it's kind of a standard pin stack that a lot of CubeSat components will all connect to together. And the idea is they're all going to share a common ground. They're all going to share a common 5 volts and 3.3 volts. They'll all share a common I2C and UART, stuff like that. So that's what all those pins are for at the bottom there. And those plugged straight into the power system, into the battery and stuff like that. Right above that, this is the burn wire connector. So a ribbon cable would plug into that, and that's how we were able to talk to the wire that burned the fishing line to actually deploy the aero boom. Right above that, you can tell that's where a coin cell battery would actually go onto the electrical board. Like I said, we're not allowed to have the Raspberry Pi powered on while the satellite is in the rocket or anything like that. And so on the opposite side, so here's where the battery goes. And then on the opposite side, there's a little integrated circuit that it's just a crystal timekeeping piece. It's just able to keep track of exactly what second it was like deployed out of the space station, and then keep track of time while the satellite's powered off. That's all that's doing. Also on the sides here, these are where the solar panel sensor data would plug into. They each have a plug, and then that would go into the satellite. And then each of those are run through an analog to digital converter on the board. And then that information is sent to the Pi so we could get information there. That's the watchdog right there up top, right next to the Raspberry Pi. And then right below that is where the GPIO pins for the Pi actually plugged in. Like I said, we used a Pi 0 on the final version of the satellite. That's what it looks like when the Pi 0 is on top of the board. So collectively, thousands of hours went into finishing gas packs. Hundreds of people worked on the project over the years. It was all worth it when we were actually able to finally send it off to NASA, put it in the integrator, which is the box that it's held in the rocket. And then that image at the bottom there is Falcon 9 launching from Florida on that International Space Station resupply mission, and GasPacs is on the rocket in that picture, which is really cool. Here's a like 2-second video of what it looks like as it's being ejected out of the space station. There's actually two CubeSats that are coming out in that video there. One of them is GASPACS, then you can tell there's a smaller one right up above that that was on the same mission as us. Here's a couple pictures that one of the astronauts actually took from inside the ISS on his cell phone, and he sent it to us afterward, which is pretty cool. This is a GASPACS as it's flying away into orbit, so that's pretty fun. Now, like actually, I'm not sure if I mentioned this yet, but we were able to get some pictures down from GASPACS. That was the original idea of the satellite, right? Is to take pictures of the Earth. And so there was actually a Raspberry Pi camera plugged into the Pi, and that's how we got those pictures taken and sent down to the Earth. So first picture that we got from the satellite looked like this. Not a great picture, right? We had it programmed where it should have only taken pictures when it was on the day side of the Earth, and that's why we kind of had those sensors from the solar panels. So it had a light sensor on the outside, and it would just be able to tell, are we in day side or are we in night side? Something went wrong for the first picture we took. You can kind of see something on the top there, but that's because the contrast was cranked way up. You couldn't really see anything on the original photo. But this is the next picture it took, and you can kind of see what that line was on the last picture. Is it's the oh, let me go back here. There we go. So that's the top of the arrow boom. The Raspberry Pi camera was placed on the inside of the compartment that the arrow boom was packed up in. So this little hole right here is where the little camera lens was sticking out of. And so that's kind of, you can see the circular bit of the inside of this container here. And that's where the picture was taken from. So you can see the arrow boom as it's deployed and as it's inflated there, causing the drag. So a couple other pictures. This one's cool. I was actually pointing down at Earth. This one's objectively the coolest picture that I got. You can see the horizon. So really cool looking. So overall, mission success after just 18 hours. All we wanted to do is prove that the arrow boom was going to slow down the rate of rotation, and it did. We were able to get that information from some accelerometers pretty easy. It was also the first ever CubeSat made completely by undergraduate students, which we're pretty proud of. And a big bonus was the Raspberry Pi as the flight computer saved us about $10,000 in development costs, which is pretty nice. We were able to get a total of 9 images down from the satellite, and we were able to have a mission success, even though we lost 3 out of our 5 solar panels due to an electrical failure. That actually wasn't our fault. It was the battery that we bought from Indurasat that was designed to work in space that didn't. But anyway, that was a bit of a bummer. But we were able to get a couple pictures down before that happened, which is exciting. I do want to touch real quick. This is kind of unrelated, but also not really. The ground station that we use to talk to the satellite. It's actually up right here behind me. I've got the live camera feed. This ground station operates at around 400 megahertz is the frequency that GASPACS was talking to us at. We're on the SatNOGS network, and SatNOGS I think stands for Satellite Network of Open Ground Stations, something like that. So I just want to shout out SatNOGS real quick because it's a pretty cool program that they have going. Basically, anyone in the world can make a ground station. Doesn't have to be as fancy as ours. It can just be a wire antenna that you like stick on your roof, and then you plug it into a software-defined radio, and then you plug that into a Raspberry Pi. They have the code all written for you. You just have to download it and like set it up and get all the settings and everything correct, right? And then once your ground station is on the network, anyone who's on the network can use your ground station to talk to satellites. But also, when you have a ground station on the network, you can use anyone else's ground station in the world to talk to satellites, which is really, really cool. Here's a world view of all the ground stations around the world that are using SatNOGs. You can tell we're on the left there. There's a orange dot and then a green dot in Utah. We're the green dot. So yeah, that's exciting. Just a quick shout out to them because it's a pretty cool program. We're going to be making another ground station with a massive dish over the next year, because the next satellite that we're making is going to operate at a higher frequency, so we'll need a different type of antenna. Once we get our ground station set up, we're going to hook it up to SatNOGs, hopefully, and we'll use that to test it out and make sure we're able to get transmissions down from some satellites. So yeah, that's exciting. I won't bore you too much about the technical details of the next satellite that we're working on. But it's a 3U CubeSat, which means it'll be 3 times the size of a GasPAX. This is how big it'll be. It'll be testing some transparent antenna technology, if that's interesting to you. It'll also have an educational outreach program that goes along with it. And the satellite has been picked for the NASA CubeSat launch initiative again. So the satellite is for sure going to space. We just have to finish making it and then hand it off to NASA, and they'll most likely do the same thing where they send it up to the space station and then deploy it from there. So yeah, that's really exciting. Um, Now, I do want to just touch real quick about the flight software that we're using for GasRats, because this is kind of relevant to what I wanted to talk about today. We are still going to be using a Pi. We'll use a Pi 02 this time, so it'll be pretty much the same thing. But instead of writing our own program from scratch, we're going to be using a programming framework called F Prime. This was designed by NASA's Jet Propulsion Laboratory. It's the same flight software that was used to control the Mars helicopter that flew on Ingenuity. So that's pretty cool. But basically, it's designed to work on any operating system, and it's designed to be space robust, and it's designed to be a redundant framework. You write all of the code yourself in C++, but it like creates the drivers and the modules and stuff for you, and just makes it a lot more of a reliable and communicable framework, I suppose. So just wanted to touch on that because that's pretty cool. Also, the outreach program that I mentioned we're doing for GasRats, pretty fun, pretty goofy acronym, but if you've worked in space, you know, you pick a fun acronym and then make the project to fit the acronym, not the other way around. So GasRats will be, it'll involve the bringing Utah students to space payload. So we'll have a bunch of outreach programs. We'll go to a bunch of classrooms around Utah. We'll talk about STEM. We'll talk about space specifically. But then also the cool part of it is any students we talk to can opt into the program, and then they'll have their names laser engraved on a sheet of metal, and then we'll just stick that on the back of the satellite. So they'll have their opportunity to have their name flown in space, which will be pretty cool. So yeah, we're excited about that. I'm happy to talk more about GasRats if you want, but other than that, that's all I've got for you. And yeah, I'm happy to answer any questions you got.
That was very cool. So many cool things in there. I guess one thing I was wondering was, like, how do you have to prove that you met all those requirements? Like, it's not going to power on when it's before it's left the space station and all that sort of stuff. So there's quite a few requirements there. Do you have to do some sort of validation matrix or like that, or they just take it your word, or what? How does that work?
Yep, yeah, no. So they have a bunch of testing procedures that we have to go through to validate that it'll be okay, and it'll make sure it won't power on before then. And then also, like I said, it has a physical switch. We don't make the switch. They like plug it into our power system, and then that's on the satellite, and then that will physically validate. And they have 4 switches, so it's like double fail-safe protected or whatever. So if one of the switches like is erroneous and goes off, then you've still got one on the same side to make sure that it's still okay there. So there's a lot of redundancy built into that, and then that'll kind of help protect it from that, if that answered your question.
Yeah, so they sort of they have to see your design. Like, how do they know you haven't put any sort of nasty code in there? Or guess they,
Yeah, they make us do a design review where we walk through all of our code. They kind of just take our word on it, but they also have people look at it, and we talk to them and communicate a little bit kind of what the structure of the code is. They're not like debugging each and every one of our lines of code there, but if something did go wrong, they know that we know that we're in a lot of legal trouble. So I guess that's protection enough.
right. Yeah, I guess they're protecting themselves by making sure that you have to wait 30 minutes and stuff like that before you
Right.
power it on and stuff like that. So I guess there's lots of um, built-in safeties there. Um, yeah, so I guess the other question I had was, so did you do any simulation, or was it all like um, sort of live testing using the actual CubeSat? Like, do you have a simulation model of that, or is it just?
As far as like running the flight software or just like the satellite in general, and like the aero boom.
Yeah, that sort of thing. So, like, obviously with the things like the space station and rocketry and stuff like that, they'll have all sorts of sophisticated simulations of what's going to happen and how everything's going to work. And they obviously have like they'd hook up the Pi to a model, simulated digital twin of the actual satellite to make sure it's all going to work. Did you guys do any of that, or did you just sort of?
Yeah. Yeah, exactly. Yeah, we do all sorts of testing. We do it's called day in the life testing, and so we just make sure it's going to be able to operate correctly. And then also we do a bunch of orbital simulations to make sure it'll look good. We do orbital simulations with the aeroboom to make sure that it'll actually decrease our rotation. We did a couple weather balloon flights actually before we actually launched the satellite, and so we'd go up. I don't remember how high, maybe 1,000 meters, maybe higher into the air. Now, it must have been higher if it was a low enough atmosphere to deploy the aero boom, right? But yeah, we tested out the aero boom. We tested out the software for it. They make us do all sorts of testing, like radiation testing before we send it up, and outgassing stuff, and vibration testing to make sure that nothing's going to break when it's in the rocket and the vibrations from launch. So yeah, right now NASA's very hands off when you get accepted for CSLI up until the moment you're like, okay, I'm ready to put me on a flight. And then you have to fill out like 50 different documents and do all the paperwork and do all the testing and stuff. So,
Yeah, that makes sense because probably a lot of groups start and they never finish. So it's like you waste the
mhm.
effort from
Yeah, that
until you
does
have a final
happen.
design. It's not worth spending much time on it.
Yeah, like I said, GasPacks was picked for CSLI in 2013, and there was a period there for like um, 6 years where there wasn't much progress being made on it. They almost dropped us from the program, but we had a really good engineer take control of the project, and he convinced NASA to keep us on for a couple more years, and he was able to wrap up the satellite and get it set up. So yeah, hopefully we don't have one of those again. But
That's really cool. So I guess one other question I had is so how do you feel like the things like the Pi and I guess generally like cheaper electronics and cheaper, you've obviously designed your own boards and stuff like that. And like 20, 30 years ago, I don't think any of us could imagine being able to do all this stuff, 3D printing and all that sort of good stuff. So imagine it's just really um, made all these sorts of group projects actually possible. Whereas, 30 years ago, like when I went to school, there's no way we could even dream to this stuff.
yeah, it's been really nice being in the position that we are, and having access to all this technology, and just having access to the internet too makes stuff so much
Mhm.
easier to research, and makes stuff so much easier to make. So it's really a good time to be building CubeSats. Yeah.
Yeah. So, what sort of job are you looking for after you finish? It's sort of you apply to NASA.
Personally, I don't know. I probably, yeah. I lied earlier when I said I'm an electrical engineering major. It's actually my degree is computer engineering, so it's like basically an electrical engineering major, but with the like computer science emphasis. So I don't know if I got something related to that, that'd be cool. If I did something in systems engineering, that'd be cool. I'm happy to get involved in anything that is involved in space for sure. So yeah.
Cool, very cool. So, a couple of questions in the chat there. So,
Yeah.
Greg asks, what was the main components? Was the main component sealed or open to vacuum?
As far as the bit where the aero boom was stored in, that was open to vacuum, and everything else with the pie and everything that was also exposed to vacuum. They don't like you having anything pressurized on the satellite because if that goes wrong, that could uh, explode, and that could like cause some problems on the rocket, right? So we were able to have the aero boom pressurized, and that was it. So
Well, does anyone want to unmute and ask their question, or should I just read them out? Anyone wants to unmute and ask their question? Go ahead.
Uh, yeah, got a question.
mhm.
Um, if F prime had not come along and you were doing this again, would you have considered using maybe three of Raspberry Pi's microcontrollers and the usual sort of agreement between three? Um, reason I'm asking for that comparison is because the power consumption could be a lot lower, and it seems like it would also address a, a few of your other concerns like radiation.
Yeah, yeah, that'd be a good idea. I know. when the GasPacks code was written, it was a very stressful wait as we were waiting for the first transmission to come down, because we were like um, we had double checked and triple checked everything worked well, but we were very worried that still there was something we had overlooked. And so if we had, it wouldn't be a bad idea to consider in the future. Um, Definitely like multiple, program or sorry, multiple computers that are all, in agreement with each other. That's something that we had considered. I think we ended up um, scrapping it for some reason or another, but I don't know if I could tell you off the top of my head what the reason for that is. But certainly with the F prime framework that we're using, that does make things a lot more reliable, which is nice. But as far as using a system like that, um, there are some definite benefits, and especially considering the size of a Raspberry Pi, it would just kind of make sense to stick three of them on there, and it's like tiny, right? So, yeah, for sure, a good idea.
If
It's not a trivial problem, is it? So that in itself is difficult. So we use those at work,
Mhm.
and we occasionally have problems, even though it's been the same technology for 30 or 40 years.
if the reasons against come back to you, I'd be interested.
Yeah, yeah, for
Okay.
sure.
And how did your boom go? Did it oscillate or did it work okay?
Yeah, it works just fine. I don't have it on me, but there exists a graph somewhere where you can see over time the angular momentum does decrease slowly, which I mean that's what we expected. That's what we were shooting for. So that was good.
Great. Thanks.
Yeah.
When's your next one going up?
Yeah, so GasRats has been in development for 2 years now, and I'm shooting to have it done and ready for launch in another 2 years, which sounds like a long time. But as far as all of the progress being done on it is engineering students who have a bunch of engineering student homework. We do the best we can with our development timeline, and hopefully it's not too ambitious to have it up in a couple of years, because we like to make sure we do stuff right, and we like to make sure we take our time with everything. So yeah, that's kind of what we're looking at right now.
And that will use the same kind of boom to kind of keep it stable, or
Yeah, so GasRats will actually not use an arrow boom. It's a technology demonstration, so it'll be testing out some transparent antenna technology, and that'll be the point of that satellite.
transparent antenna. What
Mhm.
is that exactly?
Yeah, well, like I said, this is more my area of expertise. I do know a lot about this because I have done research on it. I actually did include an extra slide in case anyone asked. So I can kind of run through that real quick if we'd like. Um,
Yeah,
Sure.
please do.
yeah, so I like I said, we were able to get 9 pictures down from GasRats over the entire mission. That's because the antenna that we were using was at, like I said, 400 megahertz, which isn't the best frequency of antenna to be sending pictures down. We actually had to break it up into multiple packets and then send those packets over multiple passes as the satellite went overhead, each to get just a single picture, right? Normally, if you're a CubeSat and you want to be sending high quality data like pictures down, you don't want to use an ultra high frequency antenna like the one on GasPacks. Normally, you use something like this. This is a picture of an S-band patch antenna. So it's at a higher frequency, closer to 2.5 gigahertz. And the idea is it's basically just a sheet of copper and then like an insulator underneath, and then another sheet of copper on the bottom. And then that kind of acts as a capacitor, and then that does electromagnetic field stuff, and then that emits an electromagnetic signal. And that's all an antenna is, right? Something that emits electromagnetic radiation, right? So this antenna has got a higher directivity, which means the gain pattern is not so much of a sphere, it's more directed, right? So you're able to get a lot more data down with an antenna like this. So the problem with using a patch antenna or a patch antenna like this, though, is if you've got a CubeSat like GasPacks, like I said earlier, you've only got 6 sides to put a solar panel on. We lost 3 out of our 5 solar panels on GasPacks, and we were barely generating more power than we were consuming before we lost just a single solar panel. And so solar panels are very, very important, especially on a smaller CubeSat. So the problem with a patch antenna like this is it's about this size, and so if you put it on the outside of your satellite, you have to remove one of your solar panels to put the patch antenna on that exterior face of the satellite, which isn't great, right, for your power generation. So the idea is we're going to make our own patch antenna completely from scratch, and we're going to redesign it so it'll instead of being a solid sheet of copper, it'll kind of have this mesh shape. So it'll have a lot of square holes on the inside of it. And then instead of putting it on a regular insulating material, we use this kind of saran wrap-like material is the consistency that it is. And then when we put them together, the antenna looks kind of something like this. You can tell that's the saran wrap-like material I was talking about. And then that grid there with all the holes in it is able to function nearly as well as a regular solid patch antenna. And then the idea is instead of swapping out this face of the satellite for a solar panel, or sorry, swapping out the solar panel to put the patch antenna on that face, we can put the transparent patch antenna above that solar panel. And so then we're able to still use that surface area for power generation, but we're also able to have a patch antenna. And this is kind of what that would look like. That's just a 3D printed solar panel underneath with a transparent patch antenna up top. So anyway, that's the idea behind GasRats. I'm pretty excited about this project. So the satellite, like I said, it's going to be about this big. It'll just have the antenna on top of one of the solar panels. It'll have another solar panel next to it as a control to see how much the antenna affects the power generation. And then you can tell there's a little Raspberry Pi camera that is going to pop out of the satellite to take pictures of the antenna. And then we'll use the antenna to send those pictures to ourselves. So it'll be taking some selfies, basically. So yeah, it's a completely separate mission from GasPacks, completely unrelated. Dr. Rayhan Bakhter, she is one of the professors here in the electrical and computer engineering department. She's done her research on CubeSat antennas for like 15 years, and she's done research on this transparent antenna technology for like 10 years. So she was great because we were looking for a new satellite to make and we needed an idea, and she was like, do you want to try out this antenna stuff? And we were like, cool. So yeah, that's the project that we're working on right now.
That looks a little bit bigger than a cube.
Yeah, so this is this is what we call a 3U CubeSat, which means it's 3 times the size of a standard CubeSat. And so it'll be 10 by 10 by 30 centimeters long. So
I don't think you're allowed to use metric in America.
yeah, NASA
Okay.
uses it. NASA uses it. So we follow what they do.
That's good to see, actually.
Yeah.
Any other
Hi.
questions?
Yeah. Hi, Ethan. Is your original satellite still up there? The boom works by drag, and you want to be tidy, right? So it's got to come down sometime. Is it still up there?
Yeah, so unfortunately, because of all that drag, it was already in low Earth orbit, which is the lowest orbit you can practically get into without deorbiting immediately. Normally, a satellite of this size in low Earth orbit will last around a year before deorbiting, but because of the aero boom and the extra drag, it actually deorbited after 4 months. So it was only in the air from January 2022 up until May of 2022. And when we hand off the satellite to NASA, they make us do all the math to prove that it'll completely burn up in reentry. So that's what happened to the satellite. It doesn't exist anymore. It burnt up sometime. So
Good.
yeah.
Cheers.
All right. I can run through some questions in the chat here. How long will it stay in orbit? That was 4 months, like I said. Thanks for the congratulations from Ian. How many people are in the team? So number fluctuates. We have usually 15 to 20 core members of the gas team that are working on the satellite all year long. We have an influx at the start of the school year. Like right now, we just onboarded probably 30 extra people to the team. Not everyone will stick around, just being the nature of a university club, but we hope everyone does because we're really excited to have everyone working on the project. So yeah. How do we launch it? Like I said, that was the NASA program. They pay for the cost of our launch. So for GasPacks specifically, it was the resupply mission to the International Space Station. Basically, NASA just if you're part of the program, they'll talk to contractors and stuff, and they'll just see if there's any extra room on any rockets. And if there is, they'll ask the contractor to squeeze us in the rocket, and that's how we get up to orbit usually. You could change this. You could use change of state packs, stabilize temperature if needed. Takes in heat while melting and gives it while crystallizing. Yeah, that's a good idea for as far as making sure we don't freeze our computer or overheat our computer. We can use something like that for sure. Yeah. All right. Is there anything I didn't address? Anything I missed? Anything else you guys wanna ask me?
Question about telemetry. What's used for as telemetry? I don't know if you actually have much telemetry.
Yeah, there wasn't much telemetry coming down from GasPacks. It had a GPS on it, so we got GPS data. We had, like I said, we had that magnetometer data to sense, and that was so we could sense how fast it's rotating through the Earth's magnetic field, and that's how we were able to get that chart where we can see the rotation slowly going down. GPS, magnetometer. I think that was it. I'm sure there was some couple other just like basic stuff that we would send down, but that's mostly what it was. Yeah.
So, given the failures you had last time with solar panels and the battery, what are you doing to address that in your next one?
Yeah, so it is unfortunate because not just because of us, but because of a couple issues with other projects and stuff like that. The company that we bought our electrical power system from, so the battery and all that stuff, they have made a new version. They don't sell the old version that broke on us. It mostly worked for most people. It didn't happen to work for us, but they made a new version. It is a lot more expensive because they spent a lot more time re-engineering it, making sure it was good. I think it was, don't quote me on this, it was something akin to a breaker going off and then not resetting itself. And so that's why we weren't able to get power generation from some of the solar panels. But yeah, it is tough because over the past couple of years, the prices for CubeSat batteries have definitely gone up, especially for the testing for the batteries. But that means they're going to end up being more reliable. We're not qualified to make batteries ourselves, especially if the satellite's going up to the International Space Station. If you make your own satellite or if you make your own battery, NASA's not gonna like that because they need to make sure 100% that it's not gonna like blow up and cause any issues, especially when there's humans on the space station. And so unfortunately that means we have to buy our batteries, which means it's gonna cost us a bit more, but hopefully that's just kind of something we have to cross our fingers and hope that whoever we buy our battery from is gonna make them correctly. So yeah.
Do you have to work to any weight limit?
Yeah, so when we go through CSLI, it's the weight limit is I think 1.2 kilograms per U is the unit, and so this one would be max 1.2 kilograms. I think it was just under a kilogram for this one, and then one for GasRat size is max 4.8 kilograms, and we won't be anywhere near that. I think we'll be closer to 2.5 or 3 kilograms weight on this one. We did not keep the receipt for the battery. I guess we did keep the receipt, but yeah, unfortunately we couldn't return it because it no longer exists. It burnt up.
Hard to figure out what actually happened.
Right.
Cool. Any other questions? Oh, well, thanks a lot, Ethan. That was really cool. That was very, very interesting. It's a really
Yeah, no problem.
interesting presentation, interesting project. To wish you luck with your degree. I'm sure you're gonna do fine. And good luck with the next satellite as well. It's really, really good.
Yeah.
Really appreciate you
Thank you.
talking to us.
Yeah.
I know it's sort of a weird time. I guess it's supposed to be around noon or something for you, isn't it? Something like that.
Yeah, around there. All good.
Cool. Thanks very much. It's very good.
All right. Thank you. I'm happy to stick around and answer more questions, or if anyone wants to email me, or you can check out our website. It's got even more details about GasPacks and GasRats and stuff too. So feel free to reach out to me that way if you think of any more questions.
Cool. Thanks a lot.